I hope everyone is checking your Hanyangin website. I think yesterday, a couple days ago, I uploaded another assignment 1.1. I think I called it as 1.1. Anybody checked yet? When is the due date? I forgot. When did I ask you to finish the assignment? 4월 2일? 4월 16일. Yeah. The first assignment should be next week. Second assignment should be on April 9th. But because of that, there is a problem on April 9th, so I put that into April 16th. 내가 16일까지 오라 그랬냐? 그랬어요? You still have plenty of time. I would discuss more on that assignment if we have a time today or sometime next class. So hopefully you can finish your first assignment sometime this week, and you can start right to the next one. Okay. Is there any problem? Why so loud? Why so loud? Okay. I hope everyone had a good weekend. Let's pick up where we left off from last class. So we were discussing throughout 2 classes, we were discussing about efficiency of a different algorithm, right? I promise you after this slide, we're not going to discuss on the algorithm part anymore, at least 2 or more classes after that. So today we're going to finish discussing on the efficiency part of the algorithm. Reason we're discussing efficiency was what? We try to compare a different set of algorithms. Basically, you want to choose the best one or choose the algorithm that suits you the best in your case, right? And then there was 3 different algorithms that we will start discussing on. What was the name of the algorithm? I forgot. Well, shuffle left, converging pointer, copy over, right? 그지? What was those 3 algorithms is doing? What was the purpose of those 3 algorithms in your textbook? 뭐였어요? What did they try to do? After a week, you already forgetting whatever we're discussing. Those 3 algorithms those are data cleanup algorithm, but basically they try to remove any zeros in the list, right? And different approach. And the first one was shuffle left. It was taking a bit longer than the other 2, but taking less space. The second one, copy over, it would take more memory, but the efficiency might be better in worst and best cases. The third one, achieve both, right? It's also good in time efficiency, also space efficiency was good too, right? Everything will be in linear time fashion. So whatever you want to do, you might want to choose the best one that you like, right? I would suggest the last one, converging pointer examples. But in terms of simplicity when you're implementing this, maybe first one is just fine too. 맞죠? That was the stuff. And then there was other algorithm. This was the algorithm we looked at. After that, we give a different ends. We try different ends if n grows really large, how each algorithm that we discussed would take, how much time it would take. Time sometimes, number of comparisons and or number of copies, number of movements within the list, right? Swapping operations that we discussed. And then pattern matching algorithm that we already know. I'm sorry, this should be multiplication, m times x. There was some typo in the slide, m times x. Pattern matching algorithm, we already know about sliding window algorithm, sliding forward. The algorithm, when we're discussing those algorithms, I also said it's like big loop, and there's another small loop inside the big loop, right? So you can basically think that it will be n squared like algorithms, right? But there is also best case in this situation too. I hope everyone remembered the sliding window algorithm for that. What is the best case for matching? You try to find a match in a given string. given long string and you given a shorter match pattern that you want to match. What might be the best case in terms of comparison, in terms of running time, maybe? 뭐가 있을까? There's only two parameters that we need to think of, like m, n, right? M, I think m was 뭐였지? M was the length of that pattern, and n is total strings that you want to match, characters. What if m and n are equal? Pattern that I'm looking for is the string that I want to match was 뭐야? A match. Should I go more? No, I can just stop right here. So if m equals n, that might be the best case. Even if it doesn't match, doesn't matter. I don't need to do more. 그죠? Only takes n comparison. I just need to simply check whether I have a matching string left over. So best case, n. Makes sense, right? Makes sense. 아니야? 맞죠? What about worst case? What could be the worst case in this pattern matching algorithm? We already discussed it. 뭐야? worst case는 또 뭐예요? 왜 그래? Wake up. 오늘 수업이 너무 많았나 보다. If I have a class in the morning, everyone is sleeping because they didn't have a good sleep. If I have a class in the afternoon, everyone falls asleep because they had too many classes in the morning. So there is no good time to have your class, apparently. Well, worst case, you try to shifting your patterns until end of the characters, which means you're doing a m comparison for n times. 그치? I need to compare m. Oh, m comparison throughout the n times. 그죠? Simply. So worst case should be. Make sense, 그죠? So two different variables, so I could just easily say maybe n-square algorithms, which makes sense. In general pseudocode, there was two loops, one smaller loop inside the big loop, right? Best case, worst case. But that solely depends on the number of, what does the input look like. So hopefully you can see the way of seeing this type of algorithm. I usually look at it, when I given an algorithm, I usually try to come up with the worst case scenario possible. So I can find out, I like to have a rough idea of, is this an efficient algorithm if I given a worst case scenario? If works well for the best case scenario, it doesn't really matter to me. So it's one way to take a look at the algorithm when you're given an algorithm right away, first time. 딱 알고리즘 이거 뭐예요 물어보면 아마 제일 먼저 나는 기본적으로 제일 먼저 하는 게 아마 여기다 어떤 인풋을 주면 이 알고리즘이 깨지나 아니면 얼마나 오래 걸리나. 그죠? That might be the first thing that you might be wondering. Okay. Hopefully that gives you an idea for the entire example that we have seen so far. But there is other cases that the algorithm that you have, your own algorithm, will be running in some crazy time. So your computer may not be finished within an hour or so. How do you determine such algorithms? So we're gonna say something like polynomial bound algorithms. If you're given an algorithm, then if you can express the efficiency of that algorithm in terms of polynomial equations. Polynomial equations, what is it? I explained once already. polynomial equation이 뭐지? 다차 방정식. 그죠? Right? n3 x to the cube, x to the power 4, 5. If you can express your algorithm running time in terms of polynomial equations, then you might have a good chance to find one. Of course, if that number is just too high, then it doesn't really matter. You're going to run into very, very long computation time. But work done is no worse than constant multiplication of n-square algorithm. Usually, n-square algorithm is a safer boundary. n-cube, you should be thinking that is there a better algorithm? Even if you have an n-square, you should thinking of any algorithm doing the exact same thing, but would take less time. So if your algorithm is polynomial bounded, then you might have a good chance to work on it. If it goes outside a polynomial bound, then you better find the other options. Graph, a collection of node and connecting edges. Graph, I don't think we would discuss a graph in this course, but it's something like this. Graph, dot, lines. So, is there an algorithm to find the path between A to C? Can you suggest me a path? Can you suggest me an algorithm that outputs the best path between A to D? 할 수 있어요? Maybe. So usually this algorithms that works on top of this type of graph takes long time. Sometimes you don't have a good algorithm in terms of time efficiency. I think somewhere in the course that we're going to cover one of the algorithm to find a shortest path in the graph. Also, you see this type of graph in where? 요즘 많이 나오는데 so much popular in nowadays. 어디서 많이 나오죠? Anybody seen from the newspapers using this type of graph? They try to understand the behavior of the people. 혹시 이런 그래프 많이 못 봤어요? 요즘에 제일 많이 나오는 그래프. 이런 그래프 나오는 거 못 봤어요? 네? 어디서 많이 봤어요? 어? 어디? 누가 얘기한 것 같은데? 마인드? 전 상당히 어려운, 맞아요. 마인드맵 맞아요. 근데 상당히 어려운 분야라 잘 몰라요. 경영 쪽에서 나올 거예요. 난 몰라. 소셜 네트워크, 트위터, 페이스북. 마인드맵도 맞아요. 근데 내가 그쪽을 잘 몰라. 그래서 미안. Your friends. You are to another friend, but this friend has also 1, 2, 3, 4, 5 friends. Friends has 3 other friends. Graph. What if I ask you to build an algorithm to find the top popular guy in this graph? Among your friends, who has the most friends? Can you come up with the algorithm to find that person? 야, 이거 어렵겠지. What would you do? What's your rough idea for building an algorithm for this? 어떻게 할까? I don't know. Maybe I can go to every single person in this graph. Maybe try to count how many lines that I have. Maybe this one has 1, 1, 1, 1, 1. This one has 5. Okay. This one has, each one has 1, 1, 1. 1, 1, 1. This one have 1, 2, 3, 4, 4. I don't know how many edges it has. 이거 몇 개나 해야 되나? 하나, 둘, 셋, 넷, 다, 여, 일곱. 아니다. 다, 여. 이건 6. 13. And then what? What would you do? I don't know it's a correct algorithm or not, but I'm just getting a rough idea. What would you do? Maybe you can do a algorithm that we studied, finding largest in the list. 그죠? I write it down 1, 1, 1, 1, 1, 1, 1, 6, 13, and then run that finding largest algorithm. Should be report back to me 13. But I'd like to know the name and telephone number of this 13. What would you do? There was a search algorithm that we studied, right? T1, N1. If T1 equals, 아니다. If this ID equals to something, then I can print out the name of the node. 그죠? So you just built one very simple algorithm. It may not be the best algorithm. It's not the best algorithm. I'm just saying could be one of the examples that you can think of. Anyway, these type of graph is also one option. And in the textbook, they try to give you another example. Hamiltonian circuit. Circuit is what? Circuit is what? What is a circuit? In Korean, circuit이 뭐죠? 회로도. So when you're designing those circuits, they use this type of graph representation and make sure that no paths overlap each other. No paths are crossing each other. This is slightly outside of this course. So I'm just gonna read it, just don't worry about it. Just understand what that is. Pass through a graph, whatever graph that you draw, that begins and ends at the same node, go through the all other node exactly once. I start from here, go, I don't know, go. I go back to the starting node while I'm visiting every other node in the graph. If you can satisfy this property, then we're gonna call that as a Hamiltonian circuit or something. There are just many different examples for this. I'm just saying it because your textbook try to refer to that particular examples. So graph, I don't think we'll be covering a graph theory in this course, but there are something like this out there. I have taken graph theory courses when I was in third year, 3학년 때, as a elective 교양 과목으로 들었던 것 같아요. 미치는 줄 알았어요. 한 학기 내내 알고리즘 얘기만 해요. 그래프만 그려놓고 알고리즘만 얘기해요. 그래프에서 여기서 여기로 가는 가장 빠른 방법은 하고 수업 끝. 다음 시간까지 그 계산해오기. So there are a set of people that try to make a living on this, studying on this type of graph. Optimization people, combinatorics people, crazy people are out there. Anyway, this is kind of sum up of the efficiency of the algorithm that we have looked at. So, what might be the dumbest way of studying this? Dumb way. 뭐야? 가장 바보 같은 방법은 뭘까요? 공부할 때. You could memorize it, just few lines, not that much. But do you really need to memorize this? 아니죠. If you understand the basics, then you don't need to memorize all these notations. It's quite obvious. It's quite obvious. So, searching in terms of searching algorithms, we're gonna put that as computation time or work as how many comparisons do you do? We're gonna put that as n. We're gonna use that as a unit of a work. How much work this algorithm are doing. So sequential search, best case 1, why? Why sequential search best case 1? 이거 되게 쉬운 거였잖아. Why was 1? 엄마? 왜 sequential search에서 왜 best case가 1이었어요? 제일 앞에 나오는 놈이 딱 맞았을 때, 그죠? The first name occurs is the name that you are looking for. You don't have to go to the next person in the list, right? 그죠? You look at it that way, it's quite easy. Binary search as well. Where does the binary search start? around the middle of it, right? So whatever you pick, it's right there. You're lucky. Otherwise, this is the worst case scenario, right? You have to go through the entire list. Likewise, for the binary search, after you hit the half, you're gonna decide whether you should go to left half or right half. Again, you start from the half, log n. We discussed this, right? 왜 그래? 거의 3시간째 하고 있는 건데 처음 보는 것처럼 이렇게 지겨워서 그렇지 너무 뻔한 거 내가 계속 얘기해서 그죠? 분명히 지금쯤에 한 절반 이상은 아 이제 빨리 넘어갔으면 좋겠는데 라고 생각하는 사람도 있을 거예요. 미안합니다. 조금만. Sorting. You try to sort a list of numbers, right? Selection sort was the one. 그죠? If you do it my way, then try to find the largest one or smallest one. You create another list, new list. You copy every single time you found one. So, shuffle left, we discussed it. Copy over likewise. Converging pointer, okay. Average case, I also told you do not worry about too much at this point. I more care about the best and worst case. Okay. Pattern matching that we discussed. Best case, linear, because size of n and m, if that equals, then you just need to do it once. You don't need to do the second step. You don't need to do any forward. Okay. Or m times n. I'm just going to simply put as n squared at some point. Okay. Makes sense. If you can draw this in your head, then I think you're pretty much done from this chapter. Of course, you need to practice at least once on each algorithm that we have looked at. I mean, I also told you to follow with your pen and pencils and try to put the numbers in where you are within the pseudocode. Do a loop few times just to make sure that you are in the right track. 그 눈으로 보기엔 쉬워 보여도 한번 이렇게 손으로 써가면서 이렇게 한번 해보라 그랬죠? Like in your textbook, they give a long list of boxes to follow. 그치? 이번 주가 몇째 번 주죠? How many weeks now? Fourth week? 네 번째 주인가? 점점 선배들하고 똑같아지는구나. 오케이? 이제 슬슬 눈에서 총기가 없어지기 시작하고. 그죠? 우리 학교 밥이 문제인가? 3, 4주째부터 밥을 먹으면 이렇게 되네. 귀찮지 이제. 그죠? Graph that I looked at, it's okay. Another type of graph, you could also ask you to build an algorithm to find something from this graph. It's okay. Don't worry about it. Let's skip. Okay, when things get out of hand, continues. So if your algorithm is exponential growth. Exponential growth는 뭐지? What is exponential growth? Something grows really, really quickly. 그죠? Do you know where they use this type of growth model? Fast. Like number of computers getting infected by internet worm grow so fast. Viruses. 그죠? 전염병 걸리는 ratio. 2 to the n. Ooh, 2 to the n. It's going to grow really, really fast. Faster than any polynomial algorithm that we have looked at so far. So, I don't know how to draw a graph, but probably look like. Right? Really fast. Or brute force algorithm. This is another term. I'm just going to read it first. One bits the problem into submission by trying all possibilities. Okay. What does that mean? Brute force. Okay. Ghost stop. You guys play any ghost stop in the hand game? No? Cell phones? Or play baduk, chess. Chess? 하기야 너무 늙었다. 장기도 아닐 거고. 고스톱 or 바둑. Okay. What is chess? For example, Oriental chess. What is chess? Chess, you play against someone else and try to beat them. Usually, my decision have an effect on the others, your opponent decision. So chess champions, the world chess champions, they can see a 6 to 8 steps after my move. 그죠? 뭐 그렇게 얘기도 많이 하죠. I'm not so sure they can do it or not. So if I do this, there are thousands of different possibilities out there. And then he can see next 8 moves ahead. So whatever your opponent makes the move, he can prepare, right? That's how you can win the chess. Me, I can only see one move after I made. Right? So if you want to play chess, you want to be a world champion, what might be the best way of doing it? You see every single possibilities. Then whatever your opponent makes move, you know. You know how to defend yourself. So if your algorithm works in that way, it tries every single possible solutions, then you're dealing with something called brute force algorithms. There are algorithms like this. Chess is one of them too. 내가 하는 거에 예를 들어 이거 찾는 거에 여기서부터도 해보고 여기서부터도 해보고 여기서부터 해보고 다 해보고 그 중에 제일 좋은 거 고르면 제일 좋은 알고리즘이죠, 그죠? 그런 알고리즘도 있어요. Brute force. What might be the downside of this brute force algorithms? What might be the bad thing about this brute force? Huh? It's gonna take a long time, or sometimes it cannot give you all the possible solutions at all. 바둑? Maybe. Intractable problems. No polynomial bound algorithms exist. So there are certain problems that you cannot come up with a good, reasonable solutions, reasonable time-efficient algorithms. If you cannot find a solution in reasonable amount of time, then there is a way to solve this, something called approximation algorithms. Approximation, what is approximation? In Korean, 뭐냐? 대략. So you try to find a solution that you think it work okay. So you come up with a couple of approximation algorithms. There's no algorithm to find the one solution for certain problems. Okay, then let's try to find the algorithms that does close enough. Like the example that I gave you was 택배 아저씨. Every morning, they have to schedule their route. Those type of algorithms to find the best path in every morning could be approximation algorithms. There is no single algorithm can give you the one only solutions, the best solutions. In your textbook at this level, they just give you the concept of it. Approximation, brute force algorithm, these type of stuff is in other areas. But it makes sense, right? 택배 아저씨 problems and chess, like those algorithms. What if I give you the assignment to come up with your own chess algorithm to beat each other? And I'm gonna give A+ to one who wrote the algorithm, the winning algorithm. 예를 들어 내가 각자한테 체스 할 수 있는 알고리즘 각자 짜오라고 그러고 여기서 그냥 시합시켜. 그래가지고 최종까지 살아남는 사람 A+. 1등부터 10등 A+, 10등부터 20등 A. 얼마나 좋아. 그럼 난 점수 매길 것도 없는데, 그죠? There was one course that I took in my university that was a course like that too. It was in AI, artificial intelligence. They study this type of algorithms in artificial intelligence. 그 뭐지? 퍼즐, 8 퍼즐. 1, 2, 3, 4 이렇게 하는 거 있지? And then you have to come up with the algorithm to 1, 2, 3, 4, 5, 6, 7, 8. 아, 이거 이렇게 하면 안 되는구나. 1, 2, 3, 4, 5, 6. So and then this was assignment 1. The second assignment was a cubic. 그 cubic 있죠, 이거 맞추는 거. But it's simpler cubic. Simpler cubic. And then after the assignment, professor was asked us to bring up the graph of the cubic, and then whoever does it fastest then gets A+. 그 기억이 나요. 아직도 기억이 나. 대학원 다닐 때인가? 4학년 때인 것 같아. 그런 과목이 있었던 것 같아요. 그래서 큐빅, 3개짜리 큐빅, 아주 간단한 큐빅 해갖고 수업 시간에 교수님이 준 그 컨비네이션 해갖고 제일 빨리 푸는 프로그램 1등, 100점, 뭐 그렇게 줬던 것 같아요. 그거는 근데 사람이 몇 명 듣지 않아서 가능했던 얘기지. 여기서 60명이 넘는데. Can you build an algorithm to solve this? If you're interested, take a look. There's even solution out there. 이거 가면 다 다운받을 수 있어요. So the algorithms that we're looking at now are very, very basic algorithms. Just try to teach you the ideas of how you're thinking, how you should start thinking about these building and solution for certain problems. 재밌겠지, 저런 거 하면. 별 재미없어요. 죽을 것 같아요. 기억도 안 나요. 10년이 넘은 얘기인데도 프로그램은 전혀 기억이 안 나고 저거 했던 것만 기억이 나요. 그러니까 별 도움은 안 돼요. 도움은 안 돼요. 물론 나는 못했지. 물론 큐빅은 못했어요. 내 알고리즘이 큐빅을 풀었겠어? 못 풀었죠. A 퍼즐까지는 했던 것 같은데 잘 기억이 안 나 이제. Okay, so in terms of growth ratio, 2 to the n square, and log n. One picture gives you the clear view of which algorithm is more efficient or not. So, quite clear graph. This n grows large there in terms of work units. So it could be comparison, could be copying operations, whatever you want to call it. Okay. And also other viewpoint, this, 이거 뭐라 그래야 되지? I don't know what color that is. 주황색이 영어로 뭐냐? Orange? 거꾸로 그건 모르겠네. Orange takes and grows more work to do. Right? Another figure try to give you in certain problems that if n is 10, 50, 100, and 1,000, log n usually takes, even if n is 1,000, they could finish the program in 0.001 seconds. Okay, n 0.12, 0.1 second. That's good. That's okay. I can still use my computer to do it. N square goes to 1.67 minutes. Okay, I can wait about a minute. So, what about 2 to the n? Exponential growth. Let's see, even 50, you're reaching up to 5,070 years of certain algorithm to solve. Where do you hear this type of time units of running a program? 저런 거 어디서 많이 무슨 영화 같은 데 보면 많이 나오잖아. 어디를 암호를 뚫는데 3,000년이 걸린다는 뭐 이상한 얘기도 많이 하잖아요. 영화 제목을 보면. Maybe. Why do you think it takes so long time to break some code or encryption? 암호 깨는데 왜 이렇게 오래 걸릴까? 경우의 수가 많아서? Yes, exactly. But you try every single possibilities. Brute force. 경우의 수 많아서. That's a dumb way, actually. You don't know the algorithm. You don't know the function calls for encryption. So you try every single possibilities. Brute force. 그죠? That's why it takes so long time to break a code. 어이구, 이건 뭐야? 4 times 10 to the 16th centuries. I don't know how many years. 10,000, too big to compute. Okay. If your program running more than a minute, then in our level, that's long time. If your algorithm runs more than a minute. I don't know, it depends on the size of your data sets, but still, that's a big job to do. So hopefully that gives you an idea of how long it takes to compute something, your algorithm, the importance of your algorithm. Right? If you can do the exact same thing, but you can come up with the n-square algorithm, you're doing a unsolvable problems. 그치? 둘이 똑같이 하는데 하나는 n to the n이고 하나는 n-square면 n-square였으면 값을 가질 수 있는데 2의 n승이면 값을 가질 수 없죠. So that's how important to see, to analyze the efficiency of those algorithms. Okay. Make sense? Make sense 안 하나. 어차피 다음 챕터로 넘어가야 되니까. Pseudocode. So chapter 1, 2, 3, almost. I think it's covering up to chapter 3. So you should be able to finish your assignment 1 at this point. Because I think I asked a few questions from chapter 3 as well. 그치? Anybody start take a look at your assignment 1 yet? 시작했어요? 이미 끝냈다. I finished my assignment. I'm sure there is few. There are a few people already finished it. I already finished the assignment 1.1. 벌써 다 했어? 1.1도 다 했어? 1.2를 오늘 내줄까?
과제 틀리면 감점 있어요?
그럼요. 근데 그래 그 뭐 어차피 그 과제는 시험처럼 틀린 거에 그렇게 민감하게 점수에 크게 반영되고 이렇지는 않을 겁니다. 대신에 자기가 뭘 틀렸고 아는지는 자기가 알아야 되니까. 내가 뭐라 그랬죠? 어사이먼트 1번 낼 때 자기 거 복사 하나씩 해놓고 내라 그랬죠? 꼭 그렇게 해요. 그러면 내가 그 답 정답을 올리면 정답이 꼭 내게 다 맞지는 않아. 답이 조금씩 방법이 틀릴 수도 있거든요. 그런 거는 감점 안 해요. 그리고 얼토당토하지 않게 영화님은 1 이렇게 찍어놓은 답이 아닌 이상에는 과정을 보여주면 그런 뭐 점수가 1, 2점씩 최종에서 차이 나고 이런 경우는 거의 없을 겁니다. 거의 없을 겁니다. 크게 신경 안 써도 돼요. 그러니까 베끼지 마. 해보는 게 중요하지 서로 베껴가지고 해봐야 아무 소용 없어요. 또 쓸데없는 얘기하는데 내가 학교 다닐 때 우리는 여기도 비슷한데 숙제를 이렇게 나무 박스 같은 데다 이렇게 냈어요. 나무 박스 같은 데 요만큼 구멍 뚫어놓고 시간 되면 거기에 딱 넣어야 돼. 그러면 밤 11시 59분에 누가 걷어가. 예를 들면 59분까지 내야 되면. 그럼 그 앞에서 밤새 기다리고 앉아요. 난 몇 분째 못 풀었으니까. 그럼 내려오는 같이 수업 듣는 애들 있잖아요. 그러면 부탁을 해요. 좀 보여달라고. 안 보여주고 그냥 넣지. 이제. 그럼 뭐 하는 줄 알아요? 난 안 했어. 난 망만 봤어, 망만. 그렇게 긴 꼬다리 어디서 구해가지고 끝에 껌 붙여가지고 이렇게 꺼내요. 그래갖고 보고 막. 근데 봐도 몰라. 내가 못 풀면 봐도 못 써요. 그러니까. 근데 진짜 나쁜 애들은 보고 꺼낸 거 지고 보고 베끼고 걔건 버려. 왜냐하면 답이 똑같은 게 들어가면 둘 다 빵점이 되거든. 진짜 못된 애들도 있었어요. 나쁜 애들이지 그거. 나는 진짜 지금도 양심적으로 얘기해서 나는 그래도 베끼진 않았어. 그냥 못 풀면 그냥 못 푼 대로 내고 그냥 빵점 맞아야지. 그런 애들 꽤 많았어. 그건 뭐 동양애나 외국애나 똑같아요. 외국 애들도 밤새 거기서 앉아서 우린 그거를 피싱이라고 그랬는데 뭐 인종에 상관없이 피싱을 하는 애들은 어쩔 수 다 합니다. 난 대학교 어렵게 졸업했어. 4년 내내 피싱하는 애들 앞에서 지켜가면서 했어. Level 1, Chapter 1 and 2 and 3, pseudocode. We discussed it, sequential, conditional, iterative. Now you know all the basics. So I'm sure you can start build your own pseudocode or even TD algorithms. Chapter 3, desirable problems for algorithm, desirable properties of the algorithms. I like to have a less time, I like to build a time efficient algorithms, right? Taking less space if possible, right? Those are the desirable properties of those algorithms that we try to build, right? Now we can start comparing between different algorithms stuff. Okay. Desirable attribute of the algorithms, correctness. Yeah, output must be correct in all cases. Assuming that the input is meeting the preconditions, input is fine. There is no input that m is bigger than n. Okay. Elegance, efficient, it's okay. Efficiency, algorithm, careful use of resources is extremely important. Extremely important. So I know it's too much for some of you. Just start thinking like the algorithms, but I'm asking you like a little bit more. When you try to come up with the algorithms, try to think a little bit on the efficiency part. That's because that's important. That's important. Okay. Any questions at this point? 질문. 아, 이제 알고리즘 벗어났다. 그죠? Done. Anybody, it's okay. I can ask you now. Anybody start reading your textbook? I haven't started yet. Raise your hands. It's okay. 책 아직 안 읽기 시작했어요. Okay. You still have a week. 자, 한 일주일 남았으니까. It's also good to start at this point. 왜 읽을 게 너무 많아? 아니잖아. 4월 1일이면 다음 주 수요일 아니에요? 맞죠? 아닌가? 4월 2일 언제지? 다음 주 수요일 아니야? 아직 시간 엄청 많이 줬구만. 난 대부분 2주 정도 줘요. 숙제는. 솔직히 일주일이면 다 되는 건데. Okay. So, let's go to the next chapter. So you can relax a little bit in this chapter, things that you already know, some parts of it. Algorithms, pseudocodes, for some people it might be brand new to you, but this one, things that we're covering in this chapter, you guys already know many stuff from this chapter. Like binary systems. Binary systems. What is binary systems? 0101. But we're living in decimal world. We're going to use 0 to 9. Okay. Translate between base 10 and base 2 numbers and represent the negative numbers using both signed magnitude or 2's complement representations. Simply put, converting numbers in 2 different digits. 하나는 이진법, 하나는 십진법. I don't think I'm going to do the examples. Everyone seems to know how to convert each part. But why you need to convert to a different units? So we're going to take a look. Or can you express a negative numbers in binary number system? Plus and minuses. Can you use binary numbers to express that? 해야 되겠죠? There must be a way to represent the negative numbers. The system. Explain how floating point numbers, characters, sounds, and images are represented in the computers. Images. What you see in your screens, or if you play games. If you play a 3D games, I don't know anybody play 3D games. Anybody have a PlayStation? Xbox? Those are nice, right? 3D, but it's also make you dizzy too. 3D players or 3D TV. Why do they require so much heavy computation to make a 3D pictures? Why? What does it mean to have a 3D pictures in your screen? Have you guys seen the movie Matrix? 매트릭스도 안 봤어? 봤지? Somewhere in the first series of the matrix, there is a certain, these people seeing a numbers floating in the screen. 그죠? That's exactly what's happening in your screen. The pictures that you saw, that's actually numbers. But that's too much. 막 그건 막 바뀌고 하는데 it's not that dynamic as it, but it's not, it's very similar. So the graph, 3D graph, you're actually looking at the numbers. Numbers in matrix, 3D matrix. matrix가 뭐지? 행렬, right? 행렬 is a just numbers, right? Number. Simple 2D matrix, X and Y. Number. 3D matrix, maybe. How can you apply that to a image creation? 그러니까 소니 플레이스테이션 엑스박스가 그래픽 카드 좋은 거 쓴다는 게 무슨 뜻이야? 그래픽 카드 왜 비싼 거 쓰는 것 같아요? 그치? 요즘에 그래픽 카드 비싼 거 사면 걔네는 CPU가 하나 더 붙어 있다 그러죠? 그래픽 카드 위에 붙어 있는 CPU 뭐 하는 애들이에요? 왜 붙어 있어? 어? 뭘 계산하는 걸까 정확히? Matrix. They multiply, add, 행렬. 더하기, 빼기, 나누기, 곱하기. So they like to have extra CPU to just do a computation of a numbers. Okay, we're going to take a look. 살면서 왜 CPU가 빠르면 좋은지 한 번도 고민 안 해봤구나. Build a truth table for Boolean expressions. This is slightly, this will be covered in your second year course of maybe computer architecture. But you can start from learning this 010 system. You can learn the basics of building your own circuit design. But we're going to touch very, very briefly. Truth tables. Determine the relationship between Boolean logic and computer hardware or computer circuits. How can you design a circuit using this 0101? Okay. Construct a circuit using some of the product circuit design or analyze simple circuits to determine the truth table. Probably not gonna do this part. Okay. Continue on that part. 재밌지 뭐. Things that you know already. Okay. About how computer works, how the computer is designed. Well, the computing devices are built on the ideas in this chapter: laptop, desktop, server, supercomputers, calculators, embedded systems, blah blah blah. 왜 있는지 몰라. Everything is binary number system. 0101. Why 0101? I mentioned also once too. Why 0101? What is the why only binary numbers in these systems? On and off, right? Electricity, only two properties. If you connect the circuit, then electricity goes 1. If you disconnect, 0, right? Very basics. How can an electric machine represent the information? Key requirement: clear, unambiguous, reliable. That sounds really like a pseudocode properties, right? Clear, unambiguous, reliable. External representation of a number for us is 10 digits. And the machineries and the using electric machines are base 2, 0101. Now we all know. So it's like this. When you press A in your keyboard, that is being translated to certain binary numbers. Binary number written in the memory, computer memory, and then that is somehow translated back to the screen, A. In the screen, when you press A, they don't show 01001. They don't do that, right? They actually translate into some figures, some graph. External representation, whatever being done within the computer, also, they will translate back to external representation. So a lot of conversion is being done within this system. 처음엔 뭐 너무 간단한 거라 넘어갈게요. Binomial 알지? Base 2 numbers. We all know how to convert a base number 2 to 10-digit numbers or vice versa. 그죠? 안 해도 되지? 그죠? 설마. 그죠? 혹시 했으면 하는 사람들은 나중에 얘기해줘요. 그럼 다음 시간에. 네, 비디오 안 찍으면 하려고 그랬는데 이건 비디오를 찍는데 하면 대한양대학교의 망신이다. 그래서 안 합니다. 그죠? Binary 0, 1, 0. Okay. That's simply conversion tables. Converting from binary to decimal, you simply number of digits by power of 2. 그죠? 2 to the 4, 2 to the 4, 2 to the 6, 2 to the 8. That's how you do it, right? Converting from binary to decimal, add up the power of the 2 where the 1 appears in the binary number, repeatedly divide, or converting from decimal to binary, repeatedly divide by 2 and record the remainder. 그죠? How do you convert 9 to a 2-digit number is 1001. 그죠? 2 to the 3, 0019. 9. 8 더하기 1, 9. What if I ask you a question like this? Build the pseudocode to converting a decimal numbers to binary number. Give me your algorithm. 뻔하지 뭐. It's quite easy. It's already given on how to do it. What might be a possible problem with this binary number system when you try to add two numbers? It's already given. But what might be the possible problem? What might be the potential problem of this approach? Okay, you add maybe 4-digit numbers. What if your addition, the output, requires 5 digits? What can you do? Just say I built a circuit. 여기 뭐로 했냐? Okay. Computer use a fixed length binary system. Okay. Maybe I built a 16-bit circuit, CPU maybe. 16-bit maybe too much, 4-bit. Using this CPU or computer 4-bit system, I like to add two different numbers. For example, what would you do? 아, 이게 너무 많다 이러면. 이렇게 하자. 와, okay. Should be here. But the system is just 4-bit. I cannot have 5 bits. What's happening? What's happening then? This is potential problem, right? In terms of bit-digit systems. 우리야 뭐 칠판에 쓰는 거니까 필요하면 그냥 쓰면 되는데, 그죠? System doesn't recognize this. They probably ignore this. They only see this as an output. 그죠? This is not right. Cannot do a addition operation. That is something called arithmetic overflow. Arithmetic overflow. When computers try to make the number that is too large for their system. 14 plus 2 with the 4 bits. 16, can you express 16 with the 4 bits? Probably not. 그죠? 2 to the 3면 얼마야? 이건가? 맞지? 맞나? 네. Right. The maximum number that you can express with this bit is 4-bit system, 2 to the 4. 그러면 그지? 0 to 15. 아, 여기 있네. 정신 나갔네. Binary addition, exactly the same example that I give you. Okay, I know that's a problem. Or how can you represent a negative numbers? Negative numbers in the system. Signed integer include a negative integer, either plus or minus. Negative. Sign magnitude notation use 1 bit for sign, the rest for the values. One way to build your system is maybe I can use 0 as a plus, 1 as a minus. I only care about last 3 digits. So 0 plus 1 minus. I only care about last 3 digits. This is what then? Make sense? Negative 0. Is there a negative 0? In the computer system, there will be negative 0. But we're just going to treat them as a 0. 말 안 되지? Positive 0, negative 0. But anyway, in this system, if I decide to build my system using this notation, then it's a promise that I made to the system. So 0, 1, 0, minus 5, 1, 1, 0, 1. At least I can distinguish between two different numbers. But the total numbers that I can represent is reduced, right? Because I only rely on last 3 bits. 확 줄죠? 4개 쓰면 16개 할 수 있었는데 3개밖에 못 하니까 앞에 거는 비트로 나가버리니까. Or there is another way of doing it too. 2's complement representation. 2's complement. Another way to represent a negatives and positives. So to make a negative number, flip every bit and add 1. Flip every bit and add 1. Okay. So plus 5 is in 4-digit system. So 0 no longer means plus, but 5, 2 to the 4, 1, 5. 그죠? 이거 여기 0는 앞에 플러스가 아니에요. 그냥 써놓은 거예요. 5를 하려면 0, 1, 0, 1. If I wanted to put that as negative 5, I'm going to flip every bit. I'm just going to say whatever they say. 0, 1, 0, 5. If I want to make a negative 5, they say flip 1 bit, 1, 0, 1, 0, and add 1. 맞네? Okay, that's going to be a negative 5. What if I add this too? What if I add this too? What might be the one? Let's say 1 plus 1, 0, 1, 0, 1, 0. Does it make sense? Right? If I do this 2's complement way, plus 5, negative 5, if you add them up, 0, 0, 0. System seems to be fine. System seems to be fine. 이게 마이너스 5 만드는 방법이잖아요. 이 2's complement way에서. 그래서 한번 궁금해서 이게 진짜로 되는지 안 되는지 플러스 5랑 마이너스 5랑 더해봤어. 0 나오지다. Makes sense, right? The system seems to be fine. So it's a 2's complement way. 2's complement way. They just give you the method of representing a negative and positive numbers in your circuits in designs. 머리 좋지 사람들, 그지? 어떻게든지 꼼수를 만들어가지고. 예를 들면 여기 앞에다가 비트를 하나 더 하면 그만큼 돈이 더 들어가고 더 귀찮아지니까. 경우의 수가 더 많을 거예요 아마 저렇게 되면. 서킷 만들 때 경우의 수가 많으면 디자이너가 더 귀찮아. 이것도 비슷한 과목을 내가 2학년 때, 대학교 2학년 때인가 했던 것 같아. 이것도 하나 기억나는 게 있잖아요. 맨 마지막 기말고사가 밤 8시인가 시작했던 것 같아요. 밤 8시인가 시작을 해서 제한 시간이 없었어. 제한 시간이 없었어. 그리고 문제도 딱 한 줄 주고 종이는 원하는 만큼 줬던 걸 내가 기억해요. 얼핏 기억해요. 그리고 조교가 앉아서 앞에서 졸아요. 조교도 힘드니까 중간중간에 한 3시간마다 한번 바꿔고. 뭐였냐면 아마 한 문제였을 거예요. 알람 시계를 디자인해라 했던 것 같아요. 서킷 알람식의 서킷을 디자인해놔요. 아무것도 없어. 문제 딱 한 줄이에요. 나중에 예제가 하나 나오긴 나오는데. 그래서 0101로 막 하는 거예요. 알람식이 아니었으면 그거였던 것 같아. 두 개 중에 하나인데 기억이 잘 안 나. 알람식이 아니면 음료수 뽑는 기계. 음료수 뽑을 때 버튼 누르잖아. 그럼 뭐가 툭 떨어지죠? 그죠? 그것도 서킷이잖아. 예를 들어 음료수 뽑을 게 10개야. 그럼 몇 비트 시스템으로 디자인하면 편하겠어? 뭐 4비트 정도면 다 커버가 되겠죠. 근데 4비트 다 안 쓰고도 하려고 그러겠지 뭐. 뭐 그런 식이었던 것 같아요. 제 기억은 안 나. 당연히 점수가 좋진 않았겠죠. 1시간 반 만에 나갔으니. 남들은 밤새 쓰는데. Scientific notation, floating point numbers using binary scientific notation. We all know how to do this, right? Base 10 numbers. You move around the digits, right, by 2, then you get the number. Exact same rule applies for the binary numbers, except your base is now changed to 2. See? This is 3.25, 3 is 11, 25, 거꾸로, 25. 아이씨, I don't care. 저런 거 괜히 하는 것 같아요. Characters are text. Map characters onto binary numbers in standard way. So if you have a 01, 01, 01, I like to see in human characters, A, B, C, D, E, F, G. So typically in two ways, ASCII or Unicode. ASCII and Unicode. Let's take a look. It's easier. ASCII table. 이게 어디 나오니? 고등학교 때 이런 게 나와요 혹시? 아닌가? Decimal, hexacode, octet. Decimal means 32, representing a space. And hexacode 32, 헥사면 16bit, 16진수. Or let's take a look at from top. Decimal 0 means no, 너는 아무것도 안 나와. 저런 거 맨날 온다? 나보고 가르치는 방법을 배워가세요. 맨날 와요. 간단하게 지워드립니다. 또 뭐 있지? Things that you might know. Like this. So 0, 1, ASCII code 48, 49, 1. So if you generate those numbers, they will be translated into inside the system means 1, 0, 2, 3, 4, 5. Each character that you see from a computer, it's mapping in this way. It's like some sort of IDs. 그죠? ID죠, 완전히. 많다, 그죠? So sometimes you want to type this special characters in your system or web page or Microsoft Word. 그죠? 이건데 키를 모르겠죠. Sometimes you don't know how these keys look like. Maybe you can find the ASCII number for that character, then you might be able to put it into your text files. 그죠? This is ASCII, this is limited. It's limited. What about Unicode? This is Unicode, much bigger tables. Unicode, when you look at the website sometimes, have you wondered how your website can display Chinese, Japanese, Koreans in the web page? Unicode. Those numbers, it's written down here, Unicode. I'm not so sure, but if I click any one of these, 이건 영어 유니코드예요. 이건 영어고, Chinese는 아마 더 많을 거예요, 유니코드. 아마 제일 많이 하는 게 아마 중국말일 거예요. 내가 그거 정확하게 잘 모르겠어. 근데 한국말도 만만치 않게 커요. 유니코드 데이터베이스가. Why? Why do you think the Korean Unicode system is also as big as the Chinese? They don't understand the system. They don't understand the system. So they try to every single combination of the Korean characters. they only memorize this shape. But in actual Korean language, it's a combination of different shape, right? 그죠? So sometimes if you try to type this is a good example. In the old systems, if you try to type this in a Korean characters, they usually said no, because they didn't have it in the Unicode back then. I'm not so sure that's the reason, but now they fixed it. You can type this in. 그지? 한국말을 그 컨비네이션으로 안 보고 유니코드 자체는 컨비네이션을 할 수가 없으니까 모든 모양을 하려고 그랬더니 자음 모음이 몇 개지? 자음이 몇 개니? 한국말. 알파벳은 몇 개니? 아무도 모르는구나. 자음 모음이 14개 뭐 이렇게 되나? 20 몇 개니? 19개. 미안해요. 나 잘 몰라. 누가 숫자 정확하게 가르쳐 줘봐. 모음 자음이 몇 개니? 모음 야, 어떻게 나도 이걸 모르지? 21개? 아 그냥 이렇게 하면 아이오랑 별걸 다 온다. 아이오인가 뭔가. 이 몇 개니? 이건 몇 개야?
이거 쌍쌍까지 포함해서 19개.
오케이. 이거. 야, 우리 다 때려치고 역사 공부부터 합시다. 이거 큰일 날 얘기다. Okay. So how many combinations is there possible? It's assuming that's 19 characters. 엄청 많겠지? 19의 모든 컨비네이션이니까. 그것도 센텐스로 쫙 붙으면 장난 아니겠죠? 그죠? 갑자기 쪽팔리네. 그걸 몰라서. 그죠? Anyway, that's a basis for the Unicode. You can certainly take a look at this in any web page you found. 그죠? 내가 일본에 취직해서 처음에 일하러 갔을 때 제일 먼저 받았던 질문이 그거였다. 일본 애가 야 도대체 왜 한글은 그렇게 많은데 니네 그걸 다 어떻게 외우니? 였어요. 일본은 뭐 가타카나만 이렇게 대충 하면 거기서 거기 때문에 외울 게 별로 없잖아요. 나중에 생각해보니까 이게 너무 멍청한 질문인 거야. 그죠? 그래서 나중에 설명해서 이 수학 공식하듯이 껴맞추는 거라고. 그러면 숫자가 상관이 없고 하나는 걸 다 그래도 이해 못해요. 일본은. 자기네 그 언어가 시스템이 틀리니까. So hopefully there will be a better way to express Korean in some time. So you can see that ASCII is 8-bit, Unicode 16 bits. That simply means there is more characters that you can represent with the 16 bits. So 8 bits limited. Okay. Binary numbering system represent a digital representation analog. 시간이 애매하다. Okay, I'm gonna stop here today. And any questions? Any questions? 질문.